Hello, everybody. Let's go. I cannot see you, but I know you are there. Yeah, this slide, our marketing guys in my company is always pushing me to include into presentation, so this is for him. We are at AMG a business technology consulting company. We are an enterprise software vendor. There are about 700 people in AMG in Poland and about 10,000 employees in a bull group worldwide. In the context of today's presentation, yeah, we are a consulting partner of the Amazon Web Services. My role in AMG is that I am mainly enterprise integration architect and also a cloud architect for cloud projects. You can see on this slide a few of the cloud projects that I'm involved in our organization. This is XL Cloud and Extreme Factory. Those projects focus on moving HPC solutions, high performance computing, into the cloud. Extreme Factory is more at the software as a service level, and XL Cloud is more on the platform as a service layer. In the XL Cloud project, we've integrated OpenStack with Opscode Chef. We've prepared pretty much the same as Amazon did with AWS OpsWorks. Yeah, and there is one project for Polish Airlines that I would like to talk a little bit more today. This project was based on AWS. The main technical goals of this project was to gain a portal which is scalable in terms of changing traffic requirements. For example, when there is an advertisement in a prime time that there are cheap prices of the flight tickets, then the traffic is 5 or even sometimes 10 times higher than common. Another requirement was to provide geo-proximity. Well, the real requirement was to provide low latency for users worldwide. Yeah, and the requirement was also to build it in a SOA architecture. From the helicopter view, the high-level architecture is quite common. We have an front-end layer, which is HTML web application designed in a responsive web design manner. And there are also native mobile applications for Android and iOS. On the server side, in the front, we have Amazon Web Services tools, which is a content delivery network, their DNS services, and load balancers. Below, there is Scalable, some kind of portal with CMS, but this is not a real portal. This is this is built in microservices manner, and it's scalable based on Spring technologies. And this is very thin layer just to present static and dynamic content. And the whole integration logic was done on Mule ESB open source enterprise service bus. This integration layer integrates the portal with a bunch of enterprise systems in Polish Airlines, and also with a database of customers and in general operational database. If you want to build a scalable website, in a public cloud, you should utilize all of those features that public cloud gives us. One of those features is ability to provision services on demand by your own. You can do it by yourself. You have an API, you have a web console, and you can do it everything yourself. Even developers can do it. In such a situation, when you are a big enterprise organization, you don't have to wait for a new hardware weeks. You don't have to wait for procurement processes and so on. You just can have it on demand. You don't have to wait days or hours for operations or infrastructure department to perform some configurations. You can provision everything by yourself. You can provision it in a few minutes. And what I've observed in our team, that then every developer starts to complain, oh, few minutes, it's so long. I've clicked on the web console or run the script to provision a new environment, and I have to wait a few minutes. It's too long. Yeah, but that's reality. The more you get, the more you want. You can have on-demand test environments. They can be available always when you need it, and only when you need it. You don't have to pay for those test environments when you do not use it. Initially, I've estimated that we will need test environment approximately 10 hours per day. The reality was quite different because we have a flexible working hour and AMG, and in our project team, the first developer started his work about 7 a.m. and the last one, who liked to enjoy to play with his children, was working after his children were sleeping. So he finished around midnight. So that costed us about 20 hours per day for a test environment. But it was worth to automate it all, because we've learned how to automate it and how to automate then a production environment and some environments that are really used, not always. For example, some performance tests and security tests and so on. Another feature of public cloud is its elasticity and scalability. I mean scalability not in terms of massively web-based sites like Facebook or Twitter. We can have a scalability also for small web applications, because when you have, for example, 2 or 4 servers that normally serve your content, and then when you have a high traffic peak, you may need 4 or 5 times more servers, and you can automate it in a public cloud. And what is more, you can pay only for that periods of time that you need those servers. In a public cloud, especially in AWS, there is autoscaling feature, autoscaling service, when you can configure that you have a bunch of web servers named as a group, autoscaling group. You can monitor, you can configure metrics you want to monitor. It can be any metric that you imagine. Then there are some that are already provided by Amazon out of the box. And you can define your own metrics. You can monitor them. Those metrics are stored in CloudWatch Amazon service, and then there you can configure a threshold that, for example, if the average CPU utilization of your web servers is above, let's say, 70%, then you want to start a couple of new servers. And then you have another threshold that if the CPU utilization or a bandwidth or latency of your requests is below some threshold, then you can kill some of the web servers. There is also a load balancer service provided from AWS that integrates with those autoscaling groups. So when there is a new instance automatically provisioned by the AWS, then it's automatically configured with the load balancer, and the load balancer starts to route traffic to that new instance. In the public clouds, usually, we have also scalable payment model. You can have multiple tiers and possibilities how you pay for your virtual instances. In AWS, for example, you can have those blue one, which are on-demand instances. You pay per hour only when you use those instances. You can have reserved instances that you pay yearly one-time commitment fee, and then the price per hour for such instance is much, much lower than on-demand instance. There are multiple tiers of such reserved instances. We can have heavy utilized instances. We can have medium and light utilized instances. It's quite complicated billing model. It's like in telco operators. It's hard to understand it, yeah, but it's worth to compute and calculate how to use those billing models that will be good for you. In our case, in our project, we calculated that we do not need medium and light utilization instances. We only need reserved heavy utilization that we run all the time, and some of on-demand instances that we start only when we have a traffic peak. In general, Amazon promotes such a pattern that you should utilize all of those types to optimize your costs. And there is another nice billing model, which is called spot instances in AWS. Those instances are instances that the price is changing all the time based on how much capacity there is available in AWS data centers. The price of those spot instances change minute per minute. And you can set up a threshold that, for example, you want to start a bunch of such as spot instances when the price is below that threshold. And then when the price goes higher and is above that, those instances will be stopped. In the public cloud providers, we usually have a global infrastructure, so we can deploy our servers not only in a one location, but in multiple geographically spread locations. Those yellow boxes are what AWS call regions, which are completely separate part of AWS cloud. Those red circles are edge locations. These are places where content delivery network have its cache. When we look a little bit more deeply into regions, each region consists of a few availability zones. Availability zone is a separate data center. In each region, there are few such separate data centers. They are located in the same country, the distance between those availability zones is about 10 to 50 kilometers about. And we can use those availability zones to have a highly available solution because there are sometimes outages of single availability zones, and it's really uncommon to have all availability zones in one region to not work. All of the services of AWS public cloud we can divide and classify in a such way that we have some global services like the global DNS service, which is Route 53. We have a CloudFront, which is a content delivery network from AWS, and those are global services available worldwide. If we create something, some resources through the services, those resources are available globally. We have regional services that are, by its nature, highly available, but when you create something in such a service, so for example, if you put an object to the S3 object storage, such an object is automatically replicated through all availability zones in this single region to have high availability. By the way, the DynamoDB NoSQL service is a very nice service, at least for me, because it's highly available. Data are spread across availability zones. And the provisioning is very nice because you don't have to think about CPU cores, how much memory do you need to run efficiently your NoSQL database. You just provision that I want a table with performance, let's say 10,000 requests per second, writes or reads. And it's provisioned, and you can change that parameter multiple times per day for each table in your NoSQL database. So you don't have to think about hardware sizing and so on. And we have also local services which are in a single availability zones. For example, when you start a virtual instance in EC2, that virtual instance is in one particular availability zone. It's not highly available by itself. If you want to build highly available services based on those local services, you have to provide that high availability through the architecture. We have in AWS a CloudFront service, which is a global content delivery network. We can use it in a typical way to provide to the users worldwide static content. In such scenario, users get static content from the nearest edge location of the CloudFront. This static content is cached there. And the dynamic content can be gathered from AWS region where you have your solution deployed. But we can also use AWS CloudFront to accelerate dynamic content. You can route all of the traffic to your website through the CloudFront edge location. For static content, it's obvious that we can use caching. And for dynamic content, we can benefit from the TCP connections optimizations, because then between CloudFront edge location and your servers, there is a connection which is a keep alive, and there is no need to set up a new connection each time somebody wants to get the content. There is also Route 53 global DNS server with a nice feature of latency-based routing. So you can put your servers in multiple locations in 2 regions in this example. And then users from one continent are routed to the nearest region. And this latency-based routing is done by this Route 53 DNS. They store the table when they see where is the best latency between which part of global network, and route your customers to the nearest one. Nearest in a latency sense, not in a geographical sense. But the question is, if we set up such infrastructure with multiple regions when we deploy our servers, how to synchronize data between them? What is more, we should think globally and not only about 2 data centers, but we should think about all regions spread across the whole world. Yeah, and how to synchronize those data between regions. There is a feature of cross-region object copy in AWS. So when we have some object in S3, we can copy it to another region. This object could be a database backup, some dump of data, and so on. Yeah, this is okay for batch synchronizing of data, but it's not okay for online data synchronization. There is also something that is called cross-region read replicas for databases provisioned through AWS. You can set up such a read replica of your database in another region. Yeah, and AWS provision it for you and maintain it for you. This is asynchronous replication, and those replicas are only read-only, so we can use it to synchronize data between regions. We can also try to do it by ourselves. First thing I was thinking about when we started the project for Polish Airlines is that, okay, so do not use the database provisioned by AWS. Just use EC2 instances, put there our own database, and try to synchronize those data on our own. Yeah, but that was really hard to do it with network latency between those regions. So we had another concept to not synchronize the data on the database layer, but to synchronize data on the application layer to data that we need to synchronize between regions, to put them into a queue, and then asynchronously get it from that queue and write in appropriate region. And that's quite a good concept, because then we do not have to synchronize all of the data. You can synchronize only those data that we need to. Yeah, and then we came up with a sharding concept to not synchronize data almost at all, but have it assigned to each region. So for example, when the customer registers to the website, he is assigned to his nearest region, and his data, his profile is kept there in this region. And what if such a user travel, let's say for a vacation, to another region? Okay, we need to synchronize only minimal information, and that information is the shard assignment. So we synchronize only information to which shard each user is assigned, and then when he's in another region, we just forward it to his region. His latency then is lower than usually, but it's fair enough for us. Yeah, another benefit of public cloud is an automation, and if you want to build a scalable web application, automation is a must. You have to do it. You have the APIs. There is concept of software-defined networks and everything, and you have your infrastructure as a code committed to the SVN or Git repository. So you have it versioned and can roll back and so on. When we think about automation, we have to balance between bootstrapping when we start an instance, or have everything prepared earlier and set in a golden image, the image of the operating system. We have to somehow balance with those two approaches. And what we've done is that we prepared an image with Java bundled inside, with Java Enterprise Application Server inside, but the configuration and deployments of our web application was not bundled in operating system image. So our deployment process looked quite similar to what was presented yesterday, how they do it in Prezi. So our Jenkins server check out the code from code repo. It builds it, tests it, deploys to the staging environment. Yes, because we use test and staging environment in an old-fashioned manner. We do not test on a production. And then when everything is okay and we decide to deploy on a production, artifacts to deploy are uploaded to S3 bucket. Those artifacts are application binaries, application configuration, because it may change, and also the deployment scripts. The scripts that actually deploy the application on a single instance are also uploaded to the S3, because those deployment scripts can also change. And then through the Jenkins, we can kill sequentially, one by one, our production instances, and then Autoscaling service of AWS recognize, oh, there is instance missing, so I have to start a new one. Such a new one instance is started based on image, operating system image from S3, and then our new application artifacts are deployed on those instances. Yeah, when we are in the cloud, we can use some cloud best practices, but also our well-known old practices still apply to designing our architecture. Yeah, as CTO of Amazon said, everything fails all the time, so our architecture should be redundant. In AWS, we can utilize multiple availability zones. You cannot see it here, but yeah, those servers here are put in one availability zone, and those are in another availability zone. And this is out of the box in AWS. We have also some global and regional services. We have DNS, Content Delivery Network, which are global services. They are highly available by its nature. There is a load balancer that is highly available by itself, and it's also automatically scalable by itself. By the way, the Elastic Load Balancer in AWS is implemented based on EC2 instances. So it scales automatically when your traffic change. The thing is that it scales not like just that, but also need to have a few minutes to recognize that the traffic is higher and it needs to initialize new instances. So the scaling time of Elastic Load Balancer is about a few minutes. And then we have web servers. We have another load balancer to load balance traffic inside our infrastructure. We should decompose our application in separate, loosely coupled components, so we can scale each of them separately. And we can have also a database provisioned by AWS. It can be SQL database, Oracle, MySQL, MS SQL, and so on. It's maintained by AWS, and only one checkbox we can use it to check. We want to have multi-AZ deployment, which means we want to have synchronous replica of the database between availability zones to have master and slave. And then when there is a problem with a master instance of the database, DNS service change to this slave instance. And all our applications can use that slave instance as a new master. And again, this is high availability. This is done through the DNS, internal DNS changes in our infrastructure. So when we have in our application some open connections to the database, then we can have some failures. But for most cases, it's fair enough to have some little failures. Yeah, and when we design for a failure, we should also test for a failure. And there is a very nice tool, Chaos Monkey, prepared by Netflix guys. Now it's open source. And this tool can test our infrastructure if it is designed for a failure. So when you give to this tool credentials to your AWS account, this tool can change something in your infrastructure and test if it still works. It can kill your instances, it can change your firewall rules, your routing rules, and so on. And you have to check if your site is still working. Netflix guys are crazy because they are using this tool on a production. Well, maybe it's not so crazy because they say that, yeah, they want to have fault-tolerant production, so they need to test production. If they test staging environment, they will be sure that they have fault-tolerant staging environment, not a production. Next best practice in the cloud is to have stateless components to scale it easily. So where to keep HTTP session? You can keep it on a server, but that's not scalable, so that's not a good solution in the cloud. We can keep it on a servers, so synchronize those data between all of the web servers. This is an old-fashioned manner. And finally, we can put those session data into separate scalable store. This store can be a cache, memory cache, like a memcache or Redis that is available in AWS. And this is what we've chosen in our project. The problem with this is that cache clusters in AWS are local in availability zones. So when is a failure of the whole availability zone, then your user can lose their web session. But for us, it's fair enough. Another solution, the promoted by the AWS, is to use their NoSQL database, AWS DynamoDB. in the cloud, when we design architecture, we should think parallel, what we can scale and how to scale it. And for example, when we have some algorithm that we need to compute something, and on the single instance, it takes 4 hours to do it. If this algorithm is scalable, we can do it in a parallel. We can run it in a parallel on 4 instances and have the same result with the same cost. This is 4 instance hours, but 4 times faster. And yes, if you know, the time is the money, so yeah, this is quite nice. In general, if you want to design applications for the cloud, you need to get out on on-premises data center to see this cloud. So you have to think out of the box how to design application that is not in your on-premises data center, but is in the cloud. And that's all for today from me. So if you have any questions, I can answer you.
So, out of your practice, do you have any reliable comparison of actual cost of the on-premise data centers versus cloud for a large-scale portal or any other application, large-scale application?
It's hard to compare because there are different requirements. For example, if you want to have a scalable portal, scalable web application in your on-premises data center, you have to provision all of the hardware for the highest traffic. And it's hard to compare because in public cloud you pay only for what you use. So it depends case by the case. When you compare just the price of the single instance in the cloud, single instance in some basic hosting, and a single instance in on-premise, the cloud is not the cheapest one. But if you want all of that automation, scalability, and so on, yeah, the cloud is quite okay in the meaning of the price.
Yeah, can you actually give the real numbers from some actual example of such a portal? Or
there is, I don't remember, I don't have numbers, but there is such a portal provided by AWS. I don't remember the exact name, when you can compare the on-premise costs with the costs of infrastructure in their cloud.
Okay, thank you.
So I have a question about, because you have like cold copies, so you create your environments on the fly, so it takes some time.
Yeah.
So probably your threshold has to be like lower. So you have to do it before your machines start failing, right? Because then it's too late if you have too big traffic. So you have to like react faster, right? Doesn't that?
Yes, you have to react fast, and in general, like I said, in AWS, everything is about a few minutes to recognize that situation and to provision new instances. It depends from instance to instance, but it's from 3 to 10 minutes. And for us, for our solution, that is fair enough, because we don't have such a huge traffic changes that in 1 minute the traffic is 2 or 3 times higher. The changes are not so slow in our case, so it's okay for us. But I can imagine that there are some applications that this may be a problem, and then you have to provision those resources more quickly. You have to predict that you will have a huge traffic and do it after that. Yeah.
So thanks for that. Second question, what about DDoS? Where is the protection against DDoS in all that?
There are some basic, well, you cannot protect against DDoS, you can protect against DOS. There are some basic mechanisms at the AWS level, and if you want to have more, you need to do it by yourself, put any software on your load balancers and so on.
Okay, thanks.